it's done, and you will have to click on got it, otherwise it will not let you stay. You guys have done here?
Yes, Dr. Longla.
Let's see, how do we define the maximum likelihood? So definition, say L of theta equals to the product I from 1 through n of f of xi theta is called likelihood function. So that is just the product of the density function at each of the points. So we just plug in each of the xi's and then we multiply throughout. The little l of theta, which is log of L of theta, and then when you take that log here, it becomes sum of natural log of f of xi theta, I from 1 through n. This is called the log likelihood function. And in theory, we show that maximizing this function is same as not maximizing that one, which means that the same number that provides the same number theta that provides the maximum to this function is the one that provides the maximum to this one. Why is that? Because the natural log is a one-to-one increasing function. That makes sense?
Yes.
Which is the reason why most of the time in statistics, you will never see anybody dealing with this function when looking for the maximum, looking for the theta that gives the maximum, because it's much more easier to handle sums than products, right? And so the MLE is defined as the value of theta that provides the maximum of M of theta. It is obtained by solving derivative with respect to theta of L of theta equals 0, then the second derivative test. Using d2L of theta over d theta squared at theta equals theta hat, which is the solution of that. So when you solve this equation, the solution that you find, if you call it theta hat, you take the second derivative, do the second derivative test. And if the second derivative test, you plug in here, you find that this thing is negative. Then it being negative tells you that at the point theta hat, you have the maximum, a maximum of the function capital L of theta. Okay. And why will that be the case? I always ask to check at this example of the parabola. When you take a parabola, you have two directions for the parabola. A parabola is either this or that, right? The parabola that is up there will have equation ax squared, where a is positive, right? And the parabola down here will be bx squared with b negative. Everybody agrees with that? This one can actually, let me just put this here to make sure it's clean. I'm not putting other things. I could have actually plus something there, but it's not that important to have something on top. It's the direction that I want you to see. So if the parabola looks down, then b is negative, and therefore you have a maximum. And when a is positive, you have a minimum. Notice that if I take derivative twice, what I get is 2a. What I get is 2b. That's exactly this test that I'm doing there. So if you ever forget what's the direction here, you can orient yourself by the parabolas that I have here. Are we good? Let's see, we have an example. F x theta equals e to the minus x over theta, x positive, for example. Then in this case, capital L of theta will be product of e to negative xi over theta, which is e to negative 1 over theta sum of xi. Agreed? And that says that little l of theta, we take natural log, it becomes negative 1 over theta sum of xi. Yeah, I'm missing something here. 1 over theta. And so that'll be 1 over theta here. 1 over theta to the power n. And then this would be minus n natural log of theta. Otherwise, if I don't have 1 over n here, this is not a density, right? And so now we do dl over d theta. Here it's gonna be 1 over theta squared sum of xi's minus, and here that's minus n over theta. And if you set this equal to 0 and you solve, you get theta equals sum of xi's over n, and then that's equal, that's what we call x bar.
Excuse me, Dr. Longla.
Yes, sir.
In that last line, right? What's the symbol in the beginning? It's a bit blurry.
Here,
Yeah.
derivative of L with respect to theta.
Oh, okay. Oh, all right. Thank you.
Okay. And so we got that in this case, the value that, the possible value that gives the maximum is theta equal x bar. To confirm that it is the one that gives the maximum, now we need to do the second derivative test. So we need to take the derivative of this now, and then plug in what we just found here. If it's negative, then we conclude that we have it. So let me put that down up here. So second derivative test d2L over d theta square, what is it? So derivative of this thing is going to be minus 2 over theta cubed, right? Does everybody agree with that? So I'll be minus 2 over theta cubed sum of xi minus, and the derivative of this one is minus 1 over, so it becomes plus n over theta squared. And now you can replace theta by x bar. If we do replace theta by x bar, what do we get here? Minus 2 the sum of xi cancels one time here. You get n over x bar squared. We agree with that? That's for getting rid of this sum of xi with one of the sum of xi's, the n goes up, plus n over, and theta is x bar squared, and you see it's the same thing, so it's minus n over x bar squared, and no matter what you have as x bar, this thing is negative. Agreed? So that's what you got, and therefore you can really conclude that X bar is the MLE in this case. And it is unique because you found only one. Is there any question? Okay, so from here, I want to introduce the next thing that is related to this topic. Which we call the Fisher information. Define I of theta as the expected value of derivative with respect to theta of natural log of f of x theta. This is kind of the density of the family that we just used, just that inside it's not little x, but x replaced by the random variable to compute the expected value, okay? And this is the definition. And then an alternative formula for that is negative expected value of the second derivative with respect to theta, natural log of f of x theta. So these two are equal under what we call the regularity assumptions. When they are met, then these two are equal. And the most important thing for us here is not that they are equal, but it's how it is used and why it is important. Take this same example that we had. And f of x theta equals 1 over theta e to the x over theta. So natural log of f of x theta is x over, this is minus x over theta minus natural log of theta. And so d over d theta of natural log of f of x theta is the derivative of this with respect to theta. So that is equal to x over theta squared. And the derivative here is minus 1 over theta. So if I want to use this to find the Fisher information, I will have I of theta equals expected value I take this computation and I replace little x by capital X, that becomes capital X. I missing a square here, okay. That becomes capital X over theta squared minus 1 over theta squared. That's what would be on this side. And if I want to take that formula to compute, then I will need to take the second derivative here. So I need to take the derivative again, and here it's gonna be minus 2x over theta cube, right? Minus minus plus 1 over theta square. Everybody agrees with this?
Yeah.
And so here I would be computing I of theta as expected value and minus. So that will be minus expected value of minus 2x over theta cube plus 1 over theta squared. Okay. So what do we get here? Minus and minus, that becomes a plus 2 over theta cubed expected value of x minus 1 over theta squared. And so what is the expected value of x for this distribution? It's the exponential distribution, the expected value. I'm assuming it's gonna be theta. So this whole thing is gonna be 1 over theta squared. That's if you compute on this side. Now, if you want to compute on this other side, you're gonna open the parenthesis and compute. Or we can also say this is equal to 1 over, and here, what is this? Theta to the fourth expected value of x minus theta squared. But theta is the mean, so expected value of x minus theta squared is the variance. And what's the variance? What is the variance of the exponential equal to? It's equal to theta squared. So when you compute that, this here is theta squared. So you end up with that same answer you got there. What I just said is this is 1 over theta to the 4 times theta squared, because this is the variance of x. And for this distribution, the variance is theta squared. Are we good with this example?
Yeah.
Do you need me to derive that variance and this expected value?
No.
No. So
Oh, I had one question. So, is this Fisher information applicable for like all general probability density functions, or it needs to have certain properties?
And it has regularity conditions that you have to put on it. So we will be talking about that in general. It's
Oh,
just
okay.
on this example, they work.
Okay.
Professor,
Yes.
sorry to interrupt. Can you just give me that why give me the explanation that why is the expected value of x is what is the value of expected value of x
Why it is theta?
and why it is theta? Yeah. Yes.
Okay, so there are two things, either direct computation or send you to something else, but let's try just do direct computation here. Expected value of x, what is it here? It's integral from 0 to infinity. The density is this times x, right? One over theta e to negative x over theta dx, right?
Yes.
But if you want to compute this, you can see that this 1 over theta can go into dx, but the x that is here will be missing a 1 over theta. So I can put a theta out there, and this be integral of u e to negative u du, where u is x over theta, right?
Yes.
0 to 1. But yet this integral is 1.
Mm. This integral is one. Mm. That's why this is theta. And what will be the equation for variance?
Well, that's the variance by definition is variance of x is expected value of x minus expected value of x squared. But we got the expected value of x is theta. So theta, x minus theta squared. So this is really the variance, right?
Yes.
Okay. And and we can play the same game that we played here to find that this is integral 0 to infinity of x minus theta times 1 over theta e to negative x over theta is a square dx. We played that same game, send the theta inside there, do u substitution, and then computing the integral afterwards. But the difference now is that when you play that game here, x is squared, right?
Yes.
So what is coming out is going to be theta squared.
Okay.
Does that make sense?
Yes.
So here, when we do the same thing we just did in the other one, you get theta squared integral 0 to infinity. And here you're going to have x over theta minus 1 squared.
Professor, the camera need to be a little bit fixed so that we can see. Thank you,
Sorry.
Professor.
And so when you do this, you get theta squared integral 0 to infinity. And now this becomes u minus 1 squared e2 minus u du, right? And this is 1.
Thank you, Professor.
All right, so technically on this example, I just wanted to use this example to show, okay, this is an example where the assumptions of this equality hold, and you can see that they are indeed equal as said in the formula up there, right? That these two things are equal and equal to the Fisher information.
Oh, Dr. Longla.
Yes, sir.
So Fisher information is that I theta, or it's that the expected value of the derivative equals to negative expected value of double derivative.
it's equal, the Fisher information is I of theta, by definition equal to this. And under the conditions that I'll give you later, it's also equal to this.
Oh, okay.
So no matter how you choose to compute, as I'm showing you in this example, whether you compute it this way or that way, you get the same thing when those conditions are satisfied.
Oh, so it's the value in I theta. Okay.
So the Fisher information we got for this example is I of theta equals 1 over theta squared. And why is this thing important? You assume that x1 all the way to xn is IID from f x theta for theta belonging to a given set omega, and the regularity.
Can you raise the paper, please?
Yeah, the problem is I'm not seeing all the time. Sorry for that. So make sure you remind me if you see something like this, that when you see that, it means I'm not seeing your screen. So assume that x1 through xn are IID from f of x theta for some theta in omega, and the regularity conditions are satisfied for y equals u of x1 up to xn, such that expected value of y equals k of theta we have variance of y is larger than or equal to k prime of theta squared over n I of theta. So I of theta is something that allows us to have a lower bound on the variance of functions of the random sample. This says that the variance could never be smaller than k prime of theta squared divided by ni of theta. For example,
Professor, can you please tell us what are the regularity conditions?
yep, we'll get there. And just working on the example to get in there. And okay, so we are all working everything on one single example. to see what we are talking about. Because if we just take that theoretical thing and go over and over, we might be just wasting time. Okay. We haven't checked any of it, but I'll just tell you, believe that in this example, they are satisfied, right? So we continue with the same example that we have. So on this example, on our example, I of theta, what is it? 1 over theta squared. Take y equals x bar. Is that a function of the xi's? Yes, right? What is the expected value of y? What is the expected value of x bar for such a population? Always the sample, the mean of the sample mean is always equal to the population mean. Right? So it's always equal to the expected value of x. And the expected value of x, we computed it up there. It's theta. So this is the k of theta. That's the k of theta of the theorem. Y is expected value of y, which is x bar, equal to expected value of x, because x bar is 1 over n, x plus x plus x, x1 plus x2 plus x all the way to xn. And they all have the same mean. Each of them has a mean theta. So you get n theta over theta, which is theta. Are we good? All right. So this is therefore, because we said expected value of y equals k of theta, a function of theta. That's all it means. So we computed it's theta, so it's the function of theta is theta. K prime is the derivative. So what is k prime of theta? In this case, it's 1, right? So this theorem says that variance of y bar is larger than or equal to 1 over n times one over theta square, which is theta square over n. Right? Now, because we are having here x bar is the sum of independent observations, sum, and the variance of a sum is the sum of variances when it is independent. So what I'm leading to is to tell you that this thing that we got here is actually exactly equal to the variance of y in this case, which would in other words mean that this thing is the smallest possible that you can have, that x bar is giving you the smallest possible variance. Because we found a function that gives you, that hits that smallest value that you have down there. Among linear functions, that would be the smallest that you get there. Because the variance of anything is going to have to be larger than that of k prime square over this. And in the specific case of x bar, you are hitting exactly that equality. Now, what are the regularity conditions?
Excuse me, Dr. Longla.
Yes, sir.
So that I theta is calculated from f of x,
Yeah.
and the k theta is computed from another function y equals to some fx, right? Another function.
Y is u of x1 through xn.
Mhm.
Any function of this random sample that you have.
Oh, okay. All right, thank you.
Mhm.
Professor, that means
Yes.
variance of y uh, bar is less than equal to variance of x bar. Is that the last line it is showing?
This is y. There's no bar on y. I'm writing this.
Oh, variance of y is
Larger, not equal to, and I'm just writing this.
greater than equal to variance of x bar. Last thing is x bar.
No, this is exactly equal because the variance of x bar is exactly this. So this is from the theorem. From that theorem, I established this inequality, but I'm telling you that it's actually exactly equal in this case because the variance of x bar, which is what y is equal to, is exactly theta squared over n. Are we good? Does that answer your question? Can you hear me?
Yes, Dr. Longla.
I was asking if her question was answered. Okay. Now, okay, let me list you the regularity conditions though. So, I mean, the first thing is that for theta 1 not equal to theta 2, the distributions are different. Okay. So if you take, this means if you take two different values of theta and then you get two different distributions, that's what it means. It doesn't mean at some point X, but for all of them. For all theta in omega, this f of x theta has the same support. Support meaning what? The set of all points x for which the density is not equal to 0. The point of interest is an interior point. Which means it's not on the boundary. All of this, of course, is satisfied for the distribution that we were using, because in that distribution, the condition is theta larger than 0. So omega is the set open from 0 to infinity, which is the reason why any point of that set is an interior point. And by definition of that density, you cannot have the same density for different points. And the support the support of the density is same for all of them, because the condition is x larger than 0. So it's always from 0 to infinity, doesn't change based on theta. Any question? Is there any question?
No, sir.
So these other conditions are for the equality that I wrote here, that I wrote for the two forms of the Fisher information. So f of x theta is twice differentiable as a function of theta. And that would be the reason why here you can find the second derivative. That's just that condition for that. And the last one being that the integral of f of x theta dx can be differentiated twice under the integral sign as a function of theta. And that's the reason, that's also the reason why. So number 3 allows you to take this derivative. And number 4 is actually to set these two things equal as well, because you take the derivative under the integral here to get to that guy. So it's just considerations for calculations. And if they don't hold, therefore the two equalities, the second equality doesn't hold, and therefore if you use this formula to compute, then you use that to compute, you will not find the same answer if R3 and R4 are not satisfied. Now, any question at this point?
No, sir.
That theorem is called the Rao Drama Inequality.
Can you say that again?
I said the inequality that is given in the theorem is called the Rao-Kramer lower bound, Rao-Kramer inequality. Now definition. So let Y be an unbiased estimator. We know what an unbiased estimator is. Y is called an efficient estimator of theta if and only if variance of Y attains the Rao-Kramer lower bound. Which means what? Oh, variance of Y is equal to 1 over. So if you can have variance of Y equals 1 over.
Professor, can you move the camera?
We good?
Yes, sir.
All right, thank you. So if we have that variance of Y is equal to 1 over Ni of theta, where Y is an unbiased estimator of theta, unbiased estimator of theta, meaning that the expected value of Y is equal to theta. That's what it means. Just exactly as in the example that we just used. The expected value of Y was equal to theta. So it was an unbiased estimator. And so it is an efficient estimator. So X bar is an efficient estimator of theta in the problem that we use to explain this thing.
So the other part, the derivative of k theta squared, like it's gonna be 1.
Can you repeat that again?
So earlier we did, you said the Rao-Kramer lower bound is the derivative of k theta and square that and divide by the one you gave, and I theta. So the upper part is always going to be 1.
This is just a new definition. It's not the theorem. And this definition is telling you that if Y has variance equal exactly to that bound, then we say that Y is an efficient estimator. And of course, in this definition, because it says that it's an unbiased estimator, it means K of theta is equal to theta. Because K of theta is the expected value of Y. And by saying that Y is unbiased, you're claiming the expected value of Y is equal to theta.
Oh, okay.
And so K of theta is 1. So K of theta is theta. And so K prime is 1.
Oh, okay. All right. Thank you.
And it is not always obvious that even when K is 1, even when that K prime is 1, it doesn't mean that the variance of Y is equal to this. So otherwise we wouldn't have this definition. Because there are some estimators that are unbiased, but that don't achieve this. Am I making sense?
Yeah.
Dr. Longlaw?
I'm here. You're going out to that. Let's see.
Now, you need to put the paper a little bit above.
I'm just writing an example here for you guys to work through as we just did this one. Instead of trying to go further now, it should be better to have you work at one example. Let's say here X follows, that's Bernoulli. Okay. Bernoulli with parameter theta, and then we have x1, xn as the random sample IID. Find I of theta. find the MLE and get Rao Drama lower bound. Applied to the MLE. Is the MLE an efficient estimator? That's kind of a resume of everything that we did today. So apply that to this. Knowing that the Bernoulli random variable is the variable that has value 0 and 1, and you got P theta is the probability. So I'm just defining here what this means. Probability that X equal 1 equals theta. The probability that X equals 0 is 1 minus theta. That's all. Has only two values. And this is the, instead of f of x theta, that's what you have, p of x theta, right? So you use that in place of the little f in working out this example. Any success with I of theta? If this can help you, we can actually say that probability that x equal little x equals to theta to the power x times 1 minus theta to the power 1 minus x. Is the same as that. And x is 0, 1. So what we get for I of theta? Ideas? Yeah. Interact. You have an idea? Well,
Oh, I'm still looking at it.
We can take the log of that function and take the derivative of it and then take the expectation.
correct. So natural log of P of x equal x here. That is x ln of theta plus 1 minus x ln of 1 minus theta. Then we take the derivatives, right? D over d theta of that thing. What is it equal to? That's x over theta minus 1 minus x minus theta. That's the derivative. And we can see that we can take a second derivative, right?
Yeah.
To avoid having to square this and integrate. Sorry, and take the expected value, we can take a second derivative here. I'm just not putting anything in there. So second derivative can be negative x over theta squared, and here negative, that's going to be plus minus 1 minus x over 1 minus theta squared. Imply I of theta equal minus expected value of minus x over theta squared minus 1 minus x over 1 minus theta squared. And when you do that here, the minus and the minus, they cancel. That becomes a plus. So you get 1 over theta squared expected value of x plus 1 over 1 minus theta squared times 1 minus expected value of x. But for for the Bernoulli, expected value of x is theta. So that's theta over theta squared, that's 1 over theta plus, and here same thing, that's 1 over 1 minus theta. And when you add these two things, that gives you 1 over theta times 1 minus theta. So this is the Fisher information in this case. Okay, so I think we ran out of time for today, and I would recommend that you finish those questions home to prepare for the next lecture. Thank you. See.
Dr. Longlaw,
Yes.
do you have your notes from last semester? Because I took statistics